Classification models learn from data to generalize the associations between data samples and their target classes. But when data samples deviate from real-world cases or exhibit spontaneous patterns, this process can easily lead to spurious associations, thus generate systematic errors. Take a simple scenario of an image classification model to predict whether each image contains cats or dogs. Suppose this model was trained with a data set where important patterns are missing, for example, whiteness or blackness from a certain class. Or background concepts such as dog with grass background are biased towards a certain class. When deploying the model, test cases with these spurious associations will cause systematic errors over instances against those patterns such as white dogs, black cats, or cats with grass background. Despite its consequences in practice, such blind spots are difficult to capture the interpretable patterns around them, reason about spurious associations, and prevent it from generating systematic errors. To tackle these challenges, our work aims to counter systematic errors by promoting a pragmatic workflow consisting of a range of tasks to guide the inspection of spurious associations. And implementing ESCAPE, a visual analytic system for countering errors through integrating statistic and visual components to guide the inspection of spurious concept associations. As a case study, we consider the following scenario where a data scientist Mark, who wants to train a machine learning model for classifying the images of cats and dogs, aims at inspecting false predictions. Once he opened the system, he noticed in the performance chart that misclassifications with a high confidence took up a non-negligible portion compared to known unknowns. When he looked at the confusion matrix, the degree of misclassifications was indicated with the size of bigger outer circle, and the degree of unknown unknowns as the size of inner circles among all misclassified cats, which were more than falsely predicted dogs. When he moved on to instance space, he noticed all instances are represented as circles. Confidence histograms allowed him to see the distribution of confidence score over predictions, with misclassifications colored as light or darker red bars. By adjusting the sliders, he chose instances over 0.85 of confidence score to exclusively examine unknown unknowns, and less number of neighbor instances. While he did a further exploration, he found a group of cat images with person concept that were falsely predicted with high confidence, and a group of misclassified dog images with cage. When he adjusted filters to select both true and false instances, he identified a set of images with grass densely grouped with each other. When selecting those instances, they appeared in contrastive view, which is a flowchart-like layout, shows how image patterns in for confusion cases are different from each other. Each confusion case, for example, false positive, which is misclassified cats, are represented as an arrow from true class to predicted class, and connected to the panel where images are displayed. In this case, contrastive view showed that instances with grass concept falls into two cases that were both predicted as dogs. This suggested that there could be a bias of this grass concept towards dog class. Now Jane tried to hypothesize and validate if grass concept was learned to be a pattern of dog class. The system allowed users to define concepts, which are defined with a set of segments that are semantically coherent. First, she clicked Add Concept button, and the system immediately turned to concept mining view. She selected two cases where many grass concepts appeared, and clicked the segmentation button. Once the segmentation is over, segments appeared in segment view with rectangle-shaped icons. As she browsed through segments, she found a group of segments with grass that we wanted to validate. She selected it by clicking the region of interest, then clicked the Add button. Once a concept was added, it appeared in the concept list. In the system, Concept Association Plot allows users to examine the concepts, regarding how concepts are associated with misclassifications. In the plot, the 7 concepts identified were represented as a vertically aligned pair of two circles, each representing false positive as upper circle, and false negative as lower circle. These circle pairs were plotted in the two-dimensional scatter plot, whose x-axis indicates how the concept is biased towards either cat class or dog class, and the y-axis indicates how the concept is influential towards either misclassified cats for the top half or misclassified dogs for the bottom half of y-axis. He wanted to closely examine the cage concept by clicking it. Then he found that the concept detailed view showed what are the detailed images that were most associated in the training set and test set. It was interesting that top associated images in the training set were mostly cats, but included diverse objects such as cage, wall, leash, or floor rugs. It indicated that these various objects with stripe or grid-like pattern may have been learned as a similar pattern. After the investigation, Jane decided that grass concept is the most noticeable in spurious concept association, so she clicked the Debias button to see how she can remove the unwanted concept associations. The Debias view showed how spurious associations can be mitigated, as more number of grass-associated instances are DeBiased. She selected 200 instances to be DeBiased, and checked that DeBiasing method can 56% of spurious associations.